I thank you all of you for watching my videos. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem that appeared in the CSIR National Eligibility Test held in the month of June 2023. This question is from the section Linear Algebra, and this is related to the eigenvalues of a given matrix with a given property. This question is from the part B, which is a multiple choice question, which carries 3 marks. The question ID is 704030. This question is suitable for all these examinations. Right. The given question is, let A be a 3 by 3 real matrix whose characteristic polynomial P of t is divisible by t square. Which of the following statements is true? We are given 4 options. Option 1, the eigenspace of the matrix A for the eigenvalue 0 is 2-dimensional. Option 2, all the eigenvalues of A are real. Option 3, A cube is equal to 0. Option 4, A is diagonalizable. Right. We now discuss the solution of the problem in detail. We have a 3 by 3 real matrix, capital A, with the characteristic polynomial P of x. Instead of P of t, we are accustomed to write the polynomials as P of x. So, instead of P of t, we have written P of x. Note that P of x is a polynomial of degree 3 because it is a 3 by 3 matrix with real coefficients because it is a real matrix. We are given this characteristic polynomial P of x is divisible by x square. So, P of x will be equal to x square into some other factor like x minus a. Right. This is the characteristic polynomial. If you equate it to 0, you get a characteristic equation. Then, if you solve for it, the roots are the eigenvalues. X square is equal to 0 will give you x is equal to 0 is an eigenvalue of multiplicity 2, that is algebraic multiplicity of the eigenvalue 0 is 2 and the other eigenvalue is a. The eigenvalues of a are 0 with algebraic multiplicity 2 and the other eigenvalue is a. Right. What will be the a? A belongs to R. A belongs to R. Now one may argue, what is the guarantee that A will be in R? So if not, A will be in C. A will be a complex number. And A is a complex number which is the root of the polynomial with real coefficients. Then A bar is also an eigenvalue of A. Why? Because the complex roots occur in conjugate pairs for a real polynomial. Then you will get A and A bar, and that will lead to a contradiction to the degree of P of x. Thus, A does not belong to C. Therefore, A belongs to R. Thus, what are the eigenvalues? The eigenvalues are 0 with the algebraic multiplicity 2 and A belongs to R. Thus, all the eigenvalues of A are real. Thus, we got the result, and the result is appearing at option 2. All the eigenvalues of A are real. Thus, we have proved that option 2 is true. And this is a question from part B. Only one answer is correct, and that correct answer is option 2. Thus, the question is over. The answer to this question is option 2. And that is the detailed discussion of the solution of this problem. And in the examination, when you got this one as a proof of it, and you need not worry about the other options. But our students argue, suppose this question is given under part C, then how to eliminate the other options? Okay, if that is the case, let us consider the other options. And the other options obviously are not true, because this is the option 2 is the true statement. So you have to look for a suitable counter example. That we will do it in the next slide. Yes, that's what we have. So for all the options, option 1, 3 and 4, we consider this matrix A. So let A is equal to 3 by 3 matrix 0, 1, 0, 0, 0, 0, 0, 0, A. A belongs to R, A not equal to 0. So its characteristic polynomial, please compute. It is lambda square into lambda minus A. So lambda square divides this characteristic polynomial. So therefore this matrix has the given property. Right. So for this matrix, we are asking the options. Option 3, A cube is equal to 0. Is A cube is equal to 0? So now for the above matrix A, for this matrix, take that, square it and then cube it. You will find A cube is equal to first row 0, 0, 0, second row 0, 0, 0, third row 0, 0, A cube, where A is a real number, A not equal to 0, therefore A cube is not equal to 0. Then thereby A cube is not a 0 matrix. So your assertion, your option under option 3, A cube is equal to 0 for such matrices is not true. So for this particular matrix which has the said property, but still this is not satisfied. Therefore, the option 3 is not true. So if the given property is satisfied, is it necessarily A cube is equal to 0? Not necessarily. There are matrices which satisfy this property, but still this doesn't have A cube is equal to 0. Okay, the same matrix we consider, and we go to the option 1. Right, the same matrix we have, and the property is satisfied, and its characteristic polynomial is lambda square into lambda minus A. Lambda square divides the characteristic polynomial, therefore it has the said property. Agreed. Now, the eigenvalues of this matrix A, we have already seen 0 with algebraic multiplicity 2, and the other eigenvalue is A. We go to the option 1. The eigenspace of A for the eigenvalue 0 is two-dimensional. That means to say the dimension of the eigenspace of A corresponding to the eigenvalue 0 is 2. Is it so? So take the above example only. The eigenspace of A, above matrix A, corresponding to the eigenvalue 0, by definition, the eigenspace is null space of A minus lambda I, where lambda is 0. That is, it is the null space of A. And now the dimension of the eigenspace of A corresponding to the eigenvalue 0 is the dimension of the null space of A minus 0I, and that is the dimension of null space of A. What is the dimension of null space of A? It is the nullity of A. How do we calculate nullity of A? The number of columns, 3, minus the rank of A. This is rank nullity theorem what we are using. So nullity of A is equal to 3 minus rank of A. The rank of A is 2. You can see it. There are 2 linearly independent rows are there. So it is 2. 3 minus 2, that is equal to 1. But the eigenspace of A for the eigenvalue 0 is given to be 2-dimensional, but we got the dimension is 1. Therefore, the dimension of the eigenspace of A corresponding to the eigenvalue 0 is 1. But in the option, it is given its dimension is 2. Therefore, the option 1, is not true. Option 1 is not true. Move to the next option. Option 4, A is diagonalizable. Consider the same matrix A above. And for this matrix, we have the algebraic multiplicity of the eigenvalue 0 is 2. Let's talk about the geometric multiplicity of the eigenvalue 0. By definition, the geometric multiplicity of the eigenvalue 0 is the dimension of the null space of A corresponding to the eigenvalue 0. That is the dimension of the null space of A minus 0I, which we have already calculated, and that is equal to 1. So that is as above. Now what we see, the algebraic multiplicity of the eigenvalue 0 is 2, and the geometric multiplicity of the eigenvalue 0 is 1. They are not equal. They are not equal. Therefore, A is not diagonalizable. So we are using this theorem. So a matrix A is diagonalizable if and only if the geometric multiplicity of each eigenvalue equals its algebraic multiplicity is 0. For 0, the algebraic multiplicity is not equal to geometric multiplicity for the eigenvalue 0. Therefore, A is not diagonalizable. Thus, the algebraic multiplicity of lambda is equal to 0 of A, that is 2, not equal to the geometric multiplicity of lambda is equal to 0 of A, that is 1. They are not equal. Therefore, A is not diagonalizable. Thus, the option 4 is not true. So, thus we have proved that the option 1, option 3 and option 4, they are not true. Therefore, the answer to this question is option 2. That is the detailed discussion of the solution of this problem from the section linear algebra, which is related to the eigenvalues of a given matrix with the given property. Right. I am sure that you have understood the solution of this problem. Thank you for watching this video. Now, please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We hope to meet you once again for another episode of learning. I wish you all the best. Thank you.